But what about if we change the structure around? We talked a little bit in chapter 1 about isomers, and we're going to get more in depth into isomers and isomeric alkanes. Now, unfortunately, there is not a general way to calculate the number of isomers associated with a molecular formula. So if you just are given the molecular formula, like in this table, where it just shows you the total number of carbon and hydrogens, there's not a rule for how many isomers it will form. You can see it kind of varies quite quickly. If you get to C15, you get almost 4,000. And this jumps quite high how many isomers you can have the bigger and bigger the structure goes. So in simple cases and in the cases that you will be seeing, you can just figure out the isomers by systematically moving things around and changing their composition until you identify each of the isomers. Now, the Iupac naming system is pretty rigorous for naming alkanes, and we're going to be focusing on that naming system and how we name alkanes that have these different branches and in different isomer forms. So for our first three of the normal type of alkanes, methane, ethane, and propane, you should know that these do not have any isomers. And that's just simply because there's no other way you can arrange these to form a different structure. There's no way that you can move around the carbons to form anything other than just their linear forms. And I employ you to try doing it, and you will find, especially people think propane might be able to, but no matter how you move, you connect these points. Even if I connect it this way, technically this is still just one chain, long chain of 3 carbons attached to each other. Butane is the first case of our alkanes that does have isomers. It has 2 constitutional isomers. There is the linear form. So here I've drawn it in our condensed form, but if I was to draw this in our line bond form, it would look like this. Okay, there's butane. We can also rearrange the carbons here to form isobutane, which is also called 2-methylpropane. We're going to get into naming and how we got that name from the structure, but in its line bond form, it looks like this. So again, here is linear butane and isobutane. Now, these non-linear isomers of a compound, when it has one branch, so I put the key 1 branch here, we use this term iso. This is a common term, meaning it's not the official Iupac naming system for the actual structure. We're going to be learning the official Iupac naming structure, but sometimes you will see ISO used, especially in everyday products. One thing that you probably are all very familiar with that uses this term ISO because it is an isomer is isopropane. So isopropanol, or rubbing alcohol, is a isomer form, and it uses that term iso. So again, you'll see this around, and I want you to know kind of what it is referring to. It's the nonlinear isomer of a compound. But again, this is just a common term. But here you can see this is a compound that has 1, 2, 3, 4, 5 carbons in it. So 5 is pent. and it's all single bonded. So it is a pentane is this structure. So the structure below we could call isopentane, and that's because it also has 1, 2, 3, 4, 5 carbons in it, but rearranged. Similarly, here's a structure that has 1, 2, 3, 4, 5, 6 carbons. This is hexane. And this one has 1, 2, 3, 4, 5, 6 carbons, but rearranged. So we could call it isohexane. Generally, compounds that are isomers can include 0, 1, 2, or even more branched groups. So again, our example isopentane contains only one branch on a butane chain, but something like neopentane, this is just another isomer of pentane, contains 2 methyl branches on the central carbon of a propane. We're talking about these branches, and I want to describe how we are getting the names for these branches. So here, I'm just going to draw this out so you can understand what I'm saying. This main chain is here, and it is 4 carbons long, and it has 1 branch on it. The main chain here is actually here. It is 3 carbons long, and it has 2 branches on it. Now, to name these alkyl groups, these branched groups that we're talking about, these are anything that are substitutes on a chain. So if we don't have a linear chain, if we have any kind of branch off of a chain, we call them alkyl groups. And generally, the name of them is pretty straightforward. It's going to be the size of that chain, that group, using our table from before, where 1 is meth, 2 is eth, 3 is prop, 4 is but, etc., pent, hex. But the ending in this case for a side group is going to use this YL ending. So instead of any normal single bonded chain where we have an ane ending, A-N-E ending, we're using the YL ending. So here are some common groups that could be added onto a long alkane chain. If it's just 1 carbon long, it's a methyl group. 2 carbons is ethyl group. 3 propyl. 4 butyl. And this would go on and on and on. Remember now, these have to be smaller than the main chain. They're just an additional group on a longer main chain. Now, there are a few groups that have different names. And again, this is an area where I'm going to say you're just going to have to memorize these. These are going to come up quite often. They are side chain groups that are even more branched. So they're not just a single chain side chain, they're a branched side chain. So some of these groups, for example, here, this is an isopropyl group. And the way that I am showing this is this whole structure that you can see is the group itself. And the little blue squiggle line is where the group would attach. to the main chain. So I might have some main chain here, and this is attached to it. And what I've shown on the side here in blue, I know these look like we're looking at runes or something, we're doing ancient rune history. This is the line bond form of the group. So usually I'm showing the main carbon. Here's this main carbon, and this is this main carbon, and it's two little attachments. So it forms kind of a Y structure. And then here is where it would attach. Similarly, this is sec-butyl is how you would say this. Here is that main carbon here. And it has this branch, that's this branch right here, and another branch here. And here is where it would attach. Again, this is tert-butyl. It attaches down here. And here is isobutyl. Here is that carbon there. And then it's chain, and it attaches here. Now, the reason I showed you these forms, the line bond forms, is sometimes it's easier to see it structurally like this to be able to recognize it on a chain. So you can kind of know that isopropyl always makes this Y form. This is what sec-butyl looks like. Tert-butyl has this cross form. Sometimes it'll even look like this when it's attached. So again, these are side groups that you should look at, become very familiar with, and memorize. The other types of attachments, I think, are straightforward in their naming, whereas these are not so much. Okay, so let's kind of do a test based on what we just looked like. Here is a alkane chain, a long chain. And in fact, we could figure out how big this chain is. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbon chain. So I want you to practice naming what that would be using our chart. And it has 4 different groups on it, and I have circled these groups. This is how you would look for branch chain groups. This first group here, you can see, is made up of 1, 2 carbons, and they are just a linear branch. So this would be an ethyl group. This second group here is just made up of 1 carbon. This is a methyl group. Now, these next 2 are some of our special cases. Here's one. It's made up of 3 carbons and a branch. This is a isopropyl group. And this group here, another of our special case alkyl groups. This is 4 carbons. You can see they kind of form a cross. This was our tert-butyl group. And I will point out, if this helps you remember as well, that in these special case ones, the end part here still describes how many carbons are there. So remember, this is 4 carbons, but just rearranged. So they are butyl, And this is 3 carbons, but rearranged. So it is propyl group. Now, when carbon chains and alkane chains have these branch groups attached to them, we can describe how substituted the carbon is using another type of terminology. Now, again, this is just describing how substituted a single carbon is. It could be any carbon in a chain. Using this primary, secondary, tertiary, and quaternary terminology, we can talk about how many other carbons a carbon of interest has. So in this case, you can see our central carbon has one other carbon attached to it. So it would be a primary carbon. This carbon has 2 other carbons attached to it. And these could have anything else on them. They could have whatever other groups on them. But directly attached to our carbon of interest are 2 other carbons. This is secondary, and so on. 3 carbons would be tertiary, and 4 carbons would be quaternary. Again, those groups could be any size. They could have whatever else attached to them. That part doesn't matter. It's just that this carbon has 4 bonds, and each of those bonds is to a carbon. So as an example, let's look at this structure. This is 3-ethyl 2-methyl pentane. Carbon number 3 here is marked. And if we were to classify this carbon, would it be primary, secondary, tertiary, or quaternary? So again, you want to look at how many other carbons it is bonded to. And this carbon has a bond here to 1 carbon, here to another carbon, and here to a 3rd carbon. So it is a tertiary carbon.